Hello, I'm Dominic Delosto, and I will present a novel framework for visual teach and repeat navigation that can be easily deployed to almost any mobile robot with minimal setup required. Fully autonomous mobile robots have a multitude of potential applications and have seen significant developments over the past decade, but guaranteeing robust navigation performance remains an open research problem, so applications of robot navigation in the field remain few. In contrast, biology shows us many examples of robust navigation. For instance, ants are capable of robust and generalisable navigation when foraging and returning to their nests, and this is all achieved with their extremely limited visual systems and computing power. For many tasks, though, a fully flexible navigation solution is not required. For applications such as repeated sample collection, infrastructure inspection, tool guides, or item delivery, it is typically only necessary to follow a known path. In the field of robotics, this approach is known as teach and repeat, where a human operator controls a robot along a desired path, which the robot can then follow again autonomously. Previous teach and repeat research has predominantly focused on achieving high performance in difficult conditions by using sophisticated, expensive sensors such as LiDAR scanners or stereoscopic camera setups. These approaches are associated with a high computational cost, as a large number of image features must be matched between the robot's teach and repeat runs. This limits the use of these methods with small, low-cost robotic platforms, typically those for which a simple visual route following capability would be most useful. In this work, we therefore propose a novel teach and repeat formulation that only uses a monocular camera and wheel odometry information, making it applicable to almost all robotic platforms. Our approach fully utilises odometry information paired with a correction signal driven by very lightweight visual processing. This correction signal is also decoupled from the robot's motor control, allowing corrections to be made more or less often as determined by the available computing power of the robot. We evaluate our approach with extensive experimentation on two different robots, the Consequential Robotics Miro and the Clearpath Jackal. Our navigation trials total more than 6,000 meters in challenging indoor and outdoor environments. Our method proves robust in all of these situations, as well as with low-resolution images, unreliable odometry information, and significant lighting variation. We also, for the first time, demonstrate versatile cross-platform teach and repeat without changing parameters. Here, we teach a route to one robot, transfer it, and repeat that route using a completely different robot. The first part of this approach is the teach stage. Here, the robot is driven along a desired route by a human operator. At regular distance intervals, the robot stores its current position obtained by dead reckoning integration of the odometry signal, as well as an image of the current location. Because odometry noise is integrated during dead reckoning, this map will not be perfectly metrically consistent, but it still captures the topology of the route and is locally accurate. The images here do not look natural because patch normalization is applied as a pre-processing step to increase robustness to lighting differences. Images from the repeat run should match the teach run if the robot is on the path. Differences between these images allow us to compute a correction to realign the robot. We sweep the repeat image horizontally and calculate the normalized cross-correlation with the teach image. The offset between the two images is where the correlation value is maximum. We assume that the operating environment is mostly flat and that the robot closely follows the taught path, so image offsets are mostly horizontal and large nonlinear displacements do not occur. I will now explain the intuition behind the image-based correction rules we use. For full mathematical details, please consult our paper. Additionally, Zhang and Kleeman's work provides a convergence proof for a similar correction rule. In this case, the robot is traveling between two goals from the teach run. We assume that there is a dominant object in the robot's visual field that determines the correlation-based offset. Here, it is the orange circle. If the robot is rotated slightly from the taught route, there will be an associated image offset. In this case, an anti-clockwise rotation of the robot causes the orange circle to appear to move right. So, if the robot sees this object to the right of where it was during the teach route, it should perform a correction by rotating clockwise. But this image offset is not unique to rotational errors. lateral path errors can produce similar results. In general, orientation and lateral path errors cannot be distinguished, but they do not need to be, because both elicit the same rotational correction response. This is reminiscent of the visual route following strategies of ants, who rotate to align landmarks in their current view with what they remember from last traversing a route. A long path motion can be another cause of image offsets. If a landmark is not located in the center of a robot's visual field, it will appear to move as the robot drives straight along the path. In this case, an object to the robot's left appears to move left as the robot advances. The opposite happens if the object is on the robot's right. In general, we don't know which side of the visual field dominates the correlation comparison. But when comparing to images from behind and in front of the robot, the effect will be opposite. Here, the object will appear to have moved right compared to the previous goal image, but to the left compared to the next image. So, we can interpolate between these two results to account for a long path position. The correction rule for orientation is therefore as follows. Suppose the robot thinks it is located exactly on the path, but in reality it has a rotational offset. As mentioned, we compare the current image to the previous and next goal images to estimate the orientation error, delta theta. A correction is applied by rotating the robot's goals in the opposite direction, using a gain factor, k theta. The robot then continues to head towards the goal in the frame of its noisy odometry, here shown in grey. The applied correction results in it turning clockwise to follow the real path. Even though long path errors don't directly lead to failure, as well as complicating the orientation correction, they can also cause lateral path errors if the robot turns a sharp corner too early or too late. Therefore, a second rule corrects for long path errors. Again, we suppose the robot thinks it is located between two goals along the route, but actually it is further along the route than it thinks. We now assume that image correlations will be greatest for the closest goals, after image sweeping removes the effects of orientation offset. Here, because the robot is located further along the path, it has stronger correlations with the goals ahead of its estimated position. A weighted sum of these correlation values provides a rough estimate of the robot's true location, allowing us to calculate the error in the robot's position estimate, delta p. The along path error is then corrected by either pulling or pushing away the next goal. In this case, because the correlation values tell the robot it is further along the path than it thinks, the distance to the next goal is reduced, so it is reached sooner, and the robot's estimate can catch up to where it actually is on the path. Having detailed our approach, I will now run through the testing results. Firstly, we conducted a range of indoor tests to analyze the system's robustness to noisy odometry and how important tuning the parameters was for performance. We also tested the limits of the system when using low-resolution images and minimal computation. Additionally, we tested repeating a long outdoor route to assess robustness to lighting variation and unexpected passers-by. Finally, we show that a teach run recorded on one robot can be repeated by a very different robot. We first tested on a 100-meter route in the office of the QUT Center for Robotics. A high-resolution occupancy grid map of this space was available and used for LiDAR-based localization of the Jackal robot during the runs. This was only used for diagnostic purposes as a proxy for ground truth position data and never shared with our teach and repeat system. Here we show the results of corrupting the linear odometry readings by multiplying them with the constant factor. In general, greater corruption caused greater deviation from the taught route. Failures occurred when we had to intervene to prevent the robot hitting a wall. Our approach proved robust to plus or minus 20% odometry corruption, but failed above this. This is in comparison to one open source state-of-the-art teach and repeat system, BearNav, which does not implement any along path correction. It failed already with only 10% odometry corruption. We also compare to IBVS, which does not use odometry but relies on line features in images. Being well suited to indoor environments, it was successfully able to complete the route. Additionally, Zhang and Kleeman's approach only succeeded with odometry corruption between -5 and plus 10%. Here we show how the different errors evolved over the course of the route. Overall, they increased in magnitude gradually with increasing odometry corruption, suggesting there is a broad, robust region of operation for the system. We also tested the performance of the system while varying the two correction gain parameters to assess how much tuning was needed to deploy this approach to a new robot. Overall, both key parameters have a range of at least an order of magnitude over which system performance is reliable, meaning extensive parameter tuning is not required. The default value of 100th was kept for all experiments. That the system worked without any along path correction was because this route was of moderate length, and the odometry was quite accurate. We found that 10% odometry corruption caused the system to fail consistently without along path correction. Additionally, we tested the performance of the system with low resolution images. These tests were conducted with the Miro robot instead of the Jackal along a 15-meter outdoor route. Reliable performance was achieved with images as low resolution as 23 by 8, less than 200 total pixels. This result reminds us of our biological inspiration, ants, who also perform reliable navigation with very low resolution vision. The generally computationally efficient nature of this method, combined with its ability to use low resolution images, allowed us to run the system on board even on the Miro robot, which only has a Raspberry Pi 3P Plus microcomputer. We also tested on a 550-meter long route through the Queensland University of Technology campus. Here, you can see images from the repeat run on the top and the teach run on the bottom. The route was challenging because it contained multiple transitions between outdoor and indoor environments, significant lighting variation, and members of the university walking past the robot. This area of the route in particular features a very significant lighting change, with the repeat run being free of shadows because of overcast conditions. And in this part of the route, the robot must navigate a tight walkway while remaining robust to passers-by, and then make the transition indoors, back to the starting area. Overall, we successfully repeated the outdoor run both 1 and 4 months after the teach run, and with low resolution images. This is in contrast to two state-of-the-art benchmark systems, BearNav, which failed because its image feature matching was not robust to lighting variation, and IBVS, which failed to detect a sufficient number of line features in the outdoor environment to perform corrections. In our final test, we conducted a teach run on the Miro robot in the office and repeated it with the Jackal. All parameters for the teach and repeat system were kept the same between robots. The only modification to the teach data was that the images were cropped to match the Jackal's limited field of view compared to the Miro. Despite the significantly different viewpoints and dynamics of the two platforms, the route was successfully repeated. I will now address a number of limitations with the current system, which could be addressed by further work. First is the assumption we made that position offsets from the path result in horizontal image displacement. While practically quite robust, this would not apply in non-flat environments, or when using a distorted fisheye camera lens. Secondly, the system's accuracy is reduced if there are no nearby visual features. Faraway objects will not appear to move if the robot is laterally offset from the path. This limitation is typically acceptable if high accuracy is not required while the robot is traversing a large open space. If the space then starts to narrow, image offsets will increase and errors will be corrected more quickly. Another limitation is that the system does not account for uncertainty in its position estimate, so it will not recognize if it becomes lost. Finally, the system could be improved with an appropriate obstacle avoidance capability. In our test, passers-by were able to avoid the robot easily, but this shouldn't be relied upon. In summary, we have presented a novel teach and repeat framework which only requires monocular vision and wheel odometry, making it applicable to almost all mobile robots. We have shown that the system is robust both to low-resolution images and noisy odometry, and easy to deploy onto new platforms because performance is robust across a large range of parameter values. We also ran the system on board a Raspberry Pi powered robot, illustrating its low computational requirements. And finally, without any parameter changes, we performed a teach run on the Miro robot and repeat on the Jackal, two very different robot platforms. Thank you for watching. Please check out our code, paper, and other multimedia material if you're interested. And don't hesitate to contact us with any questions.